Welcome back. Blood pressure, flow, and resistance. So we're going to talk about these guys and then we're going to do a tiny bit of math, not really anything major. But this slide is designed to just show you how these interrelate and how these come together. So blood pressure is a measure of force. We measure it in millimeters of mercury. Remember, Hg is mercury, so we're going to measure blood pressure in millimeters of mercury. And it's the force that's being exerted on the lumen of the blood vessel. So how much pressure is that blood within the vessel putting against the edge, the endothelium, the lumen of the vessel. Blood flow is defined as the amount of blood that is actually reaching the end organs being the tissues. And then resistance is the sum of all the many factors that can oppose blood flow, anything that's trying to stop blood from flowing. So we can see an increased number in the red blood cells. That condition is called polycythemia. So if we have an increased number of red blood cells, we're going to see an increased blood viscosity. If I have an increased viscosity, I've increased the resistance, and therefore I have increased the systemic vascular resistance, is that bottom box there, and that's going to affect the pressure. It's going to increase the pressure. If I have an increase in body size, such as in an obese individual, then I'm going to see an increased total blood vessel length. Larger individuals have to have longer vessels to reach all of those tissues. Increased vessel length means that I'm going to increase the resistance. Increasing the resistance means I'm going to increase the blood pressure. And then finally, on the far right, if I have a decreased vessel radius or a vasoconstriction, if I've closed down the size of the lumen, I've made the space smaller for the volume to move through, therefore I've increased the resistance, and therefore I've increased the blood pressure. Okay, so these three things, all pressure, flow, and resistance, all come together to play a role in how that blood moves. Why that's of any significance to us is what we're going to talk about here. So when we talk about cardiovascular homeostasis, we're really depending upon blood flow. But the problem with blood flow is that it's very difficult for us to measure. We can't measure flow. We don't have a little flow meter that we easily just put into a vein and it flaps and measures the amount of flow. So we measure flow indirectly, and we measure it through blood pressure. So that's what we check clinically. We check blood pressure. Why? Because it's easier. It's something we can measure without being invasive, and it's directly related to blood flow. So we're coming about the answer that we're truly looking for in a roundabout way, but we're getting what we want out of the situation. So what you need to understand is that relationship between blood flow and blood pressure and peripheral resistance is really what allows us to follow a very simple law or a simple formula called Ohm's law. And this is the Ohm's law of blood pressure. It's not necessarily the Ohm's law that you talk about when you talk about electrical conduction. So this is Ohm's law of blood pressure, and it says that blood pressure is equal to the flow times the resistance. Nothing rocket science-y there. Here's what we look at graphically when we look at blood pressure. So pressure exerted by blood on the walls of a vessel. So how much force is that moving blood putting on the wall of the vessel? It's caused by contraction of the ventricles. So remember, all of that force is coming from the ventricles. Pressure is going to be highest in the aorta. Why is it highest in the aorta? Well, the aorta is the vessel closest to the left ventricle. The left ventricle having the greatest contractile force. Therefore, the highest blood pressure is going to be in the initial vessel closest to that high force, which is the aorta. Blood pressure will drop steadily in systemic circulation the further I get from the left ventricle. That should just be intuitive. So the further I get away from the source of the pressure, that initial thrust, the lower the pressure will be. So at the aorta, blood pressure is going to be roughly 120 millimeters of mercury during systole. It's going to be roughly 80 millimeters of mercury during diastole. Please remember, systole was ventricular contraction, diastole was ventricular relaxation, or even you can use the word dilation if you prefer. But that is how we get that standard number of 120 over 80 being what we consider a normal blood pressure. Okay, so remember, we're measuring flow indirectly because of this pressure. So we need to go back and review a couple of things. One of them being cardiac output. Cardiac output was the result of a simple multiplication problem, stroke volume times the heart rate. And remember, we had other factors that can influence cardiac output. We had blood pressure. So remember that blood's going to flow from areas of high pressure to lower pressure. Remember that we could have resistance due to friction between blood cells or the vessel walls. And that brings us to this summary slide. So in this summary slide, we're looking at things that increase the mean arterial blood pressure, or the MAP, the mean arterial pressure. So we'll start up on the left in green. We can have increased blood volume. We can have skeletal muscle pumping, so a lot of skeletal muscle activity working on the venous side, or even on the arterial side for that matter. We can have the respiratory pump. We can have venoconstriction. All of those guys are going to increase venous return. Increased venous return means that I'm going to have more blood entering into that right atrium. And remember, we called that entering blood into the right atrium and that stretch that we talked about things like preload, right? So we're going to increase the venous return, which means I've got more blood coming back to the heart. We can increase sympathetic impulses and hormones from the adrenal medulla. Remember, the adrenal medulla is going to be responsible for the catecholamines, epinephrine and norepinephrine. We can see decreased sympathetic impulses. So if I decrease, the parasympathetic. If I decrease the parasympathetic impulses, what I'm actually going to do is I'm going to increase the heart rate. Increasing sympathetic impulses will do the same thing, increasing the heart rate, but will also increase the stroke volume. In any case, if I increase the heart rate or I increase the stroke volume, I'm going to increase the cardiac output. And if I increase cardiac output, I have to increase mean arterial pressure. In the blue, say we have a polycythemia situation where we have an actual increased number of red blood cells. That means I have an increased viscosity. I have more formed elements than liquid, and more formed elements means more resistance and more viscosity. Or perhaps we have, as we've talked about before, an increased body size, as in the case of an obese individual. In that case, we're going to see increased total vessel length, and we talked about how that was going to increase our resistance. And then our third option there is decreased blood vessel radius or diameter within the lumen, and that's going to be termed vasoconstriction. In any of the case, increasing the viscosity, increasing the vessel length, or decreasing the vessel radius, or alternatively you can just simply say vasoconstriction. Any of those three are going to increase the resistance, the systemic vascular resistance, and that will increase our blood pressure, our mean arterial pressure. So next up, we need to talk about control. So we're going to control that pressure and flow, and after that we're going to look at a very large feedback loop system, the big picture on autoregulation, and we'll move into that whole concept of autoregulation of blood pressure.